Yeah, so I'll start by introducing myself. I'm Kevin and I'm a lead developer in Newsweaver. And I'm actually talking, it's kind of funny with Luigi, it's another problem of scaling. It's just a different aspect of scaling, rather kind of to do with data processing as opposed to maybe from user load on the system or scaling that side of things. We're scaling from the data we ingest and the value that we get from our data. So, kind of what I'm going to go through today is maybe a bit of background of how, first off, has anybody heard of Apache Spark? Anybody used it? Not too many, so I might get away with a few things. A quick background on, I guess, how we came to use or to choose Apache Spark. I'll give an overview of Spark itself. I won't go into too much details. There's lots of good resources on the web, and can be a bit dry, so I won't go through too much. What we've learned developing Spark applications and also, or developing in the first place, and what we've learned. So before jumping in, 2 years ago I joined Newsweaver, and we were at a point where basically Newsweaver software allows people to create content and for internally within a company as opposed to externally. So you have a department of people who send out CEO updates, security, whatever it might be. So they can create that content within our system. They send out these emails, and that's the kind of core use case. That's our bread and butter. So 2 years ago, we had a growing customer base. Customers were sending about 40 million emails a month on average. We had very little reporting capabilities, and the reporting capabilities we had, that infrastructure was based on Java and on top of MySQL, was under a lot of pressure. It would have continued to go along, but the kind of decision was taken to say, look, we can do more here. Another thing, our system was mainly email based, but a lot of the people, our customers, use other channels such as video. They might use intranets, they might use social channels. So there was no visibility for them. They were creating all this content and they didn't know whether it was just going into a black hole, whether it was anyone who was listening. And so again, all those emails and all that content, and the big question that people were asking us were, how do we know if people are engaging, which is always a great word to use, are engaging with this particular content? So it was a question of, like they're publishing all this, how do they know who's not looking at their content? Not just one specific email or one specific communication, but trends over time, things like that, to give them insight to improve what they do, basically adopt a data-driven approach. So our solution that we came up to this was called Newsweaver Cross-Channel Analytics. So we, as well as emails opens and email interactions, which we were already capturing in our basic reporting, we're going to expand that out to have internet page views, video plays, social networks, and comments and likes, and ingest all that data and hopefully produce something out of it. So different metrics, different derived metrics, aggregations across many different dimensions to deliver those insights that they could use to improve their day-to-day lives and how they do their job. So that led us to Spark. What were we going to do with our existing reporting engine? We could have put more work into it. We could have made it slightly better. But at the time, Spark was gaining a lot of traction. So Spark is a fast and general engine for large-scale data processing. So it's distributed. It runs on a cluster. There's loads of cool things to it. But it all sounds a bit big data. So a question I find myself asking a lot, and people ask me, is how big do you have to be? Do you really need Spark? Like, you could have improved your Java, you could have done something with MySQL. But I guess how I characterize ourselves is really small to medium-sized data volumes at the moment. I don't think we've big data in terms of volumes, but it's not all about the volume. Like, there's other aspects to big data in that the sources of your data, where it comes from. It's not all clean cut sitting in one database. It comes from many different sources. Also, the class is a problem you're solving, so cleaning that data, real-time streaming, like the velocity, send a mailing to 1 million people, you're going to get a high burst of traffic, so you have to scale up to that. Problems such as summarization and aggregation are kind of boring, but they're big data, map-reduced problems, which, funny enough, Google were the ones who set out the framework for this. Things like unique events, counting uniques across many different dimensions and many different metrics is challenging. Also, large joins, you've got lots of different data, lots of different pieces. How do you bring them together to find out the relationships between them and kind of give higher level insight to people? So, it's not all about, you don't have enough data to be thinking about using Spark. There's other aspects to it. So, I'll give a brief history of Spark. This guy, Matti Zaharia, he created Spark for his PhD project while also creating Apache Mesos and also being one of the main contributors to Hadoop. So it's pretty humbling from my, I think, what did I do with J2ME gaming thing for my master's project. So he's a pretty prolific guy. So at UC Berkeley, and they've commercialized it as Data Bricks, the company now, which commercialized Spark. It's a top-level Apache's project. This is all in the space of like 4 or 5 years. It's the largest open-source big data community, so there's like something like 1,000+ contributors to it. And all the big guns are on board with Netflix, your Yahoos, your eBays. If you Google, if I was looking at the lineup for the Spark conference in Boston, it's happening in a few months, and it's like a who's who of all the companies, you know, going through their stories. So it's got a, you know, it's got serious backing behind it. What is it? A maybe more detailed picture, if you can see that. It sounds intimidating, but it's actually not. If you look at his original PhD paper, it's like 2 pages, and it's based here, which I'll go into in a minute what it is. But why we picked it, I guess, is, or what its characteristics that make it very attractive are. It's general. If you go with something like Hadoop, I think there's a lot of Java-based libraries around that. In Spark, you've got APIs for Scala, Java, Python. They have an R library more. A lot of their focus is on data science. It's a big angle for them, so they have a great R API. I learned it's written in Scala itself. Spark is written in Scala and Akka. I learned Scala along with Spark. I didn't have any experience of functional programming or anything. The API is actually quite easy to pick up. It's fast, so a big thing over Hadoop. Hadoop is disk based. You're reading in from disk, you're shuffling out the disks all the time. It's quite slow like that. Spark is all based in memory, so RAM is getting very cheap. Just add more RAM and do all the processing in memory, and hence you get, I think it holds the world record for sorting 100 terabytes in like 23 minutes with way less machines than the previous Hadoop record holder. So it's seriously fast, way above any needs we would have. And also flexible, so it's the kind of the top two that I really like. The flexibility, Spark can consume data from, there's connectors and data sources for everything, and they're quite trivial. You're like, just give me all the data and then Spark will deal with the rest there. You know, within a few minutes you can be consuming from Cassandra or a Postgres, like, you know, 1 or 2 lines of code. You got your data. You can then work with the traditional Spark API. They've kind of modularized it then, so on top of this core, Spark SQL is a module, which is very cool. You can use your existing, a lot of people have put a lot of time into writing Spark or SQL queries over the years. You can run your SQL query as you had it on your Spark dataset. So it'll now run in memory. It won't run against your actual database. So you get that speed increase. You get the load is now off the database. Spark streaming, another kind of a big data thing that it's really nice. Machine learning, they've got all the machine learning techniques. I'm not any expert in, I don't know much about it, but all those techniques, all those complicated algorithms, they all come out of the box with this library. So now you're not kind of going, geez, how do I do Bayes classification? Or you're like, okay, is my problem suited to it? You're not kind of focused on figuring out the technicalities. You get it out of the box. Graph libraries, I'm not sure what packages is. So they've kind of built up this ecosystem that's really, really flexible, but all built on a very simple concept. And again, going back to what I said there, like what I found over the last few years is you can really deliver value fast in it because you've got this consistent API across all these kind of top-level modules. You can jump from one, you can jump from streaming to batch very quickly. You know, you can get involved in MapReduce programming if you're writing in Hadoop. You're dealing with partitioners, mappers, all this stuff. Spark, it's like that level of abstraction over that. You can jump into streaming if you're doing a bit of batch. It's the same API. You're just dealing with data sets, but in a slightly different fashion in machine learning. So it abstracts away all that, and you focus on, okay, I have this data, how do I do something with it? Not, oh God, this data is huge, I don't know how I'm going to deal with this, how I'm going to manage this in memory, how is this going to perform? And, you know, oh geez, I've got this data over here, I've got this, how am I going to bring these together? It's very easy. Spark almost doesn't trivialize it, but it makes it a lot easier than traditionally would have been. So the use cases that it's aimed at is the kind of data integration and ETL, extract, transform, load pipelines. So you've got all this data everywhere. How do you bring it together, clean it up, maybe stick it in a data store, stick it in Hadoop. High performance batch computation, I say that's what it was developed for in the first place. Real-time stream processing, interactive analytics or business intelligence, that goes back to those ad hoc. I'll do a quick exploration, I'll bring data together in memory. Is there something worth exploring further here? Very low investment in that. You're not going, oh geez, I have to go in now and have to get another, set up infrastructure like you were saying for testing. You know, there's all these things that you don't think about. With Spark, you're like, no, I'm used to working with Spark. I'll get that data in, I'll run a quick experiment on it. I'll see, is it worth investing more time in it? And also you've got machine learning and advanced analytics, which is seen as one of their biggest selling points, that they have these libraries that can make this kind of stuff a lot easier. So from a Newsweaver point of view, it kind of ticked a lot of the boxes for 4 of those. And I say the machine learning is like, I'm waiting to find a problem that I can use it for. It's like one of these things, I have a solution, I need a problem. So I'm still kind of waiting for that. But the top 4 is pretty good. Particularly this one, we're starting to, hopefully we have all this data, we've done a lot of the basic stuff over the last 2 years. We're looking to explore further, what other value is there. Maybe I can link it up with something over here to kind of find some connection that mightn't be that obvious, that might give the user a bit more power in what to do. And after 2 years, this is what we ended up with. So this is kind of our architecture for our kind of data processing. You've got different kind of ingestion channels from like SharePoint, your intranets, to videos, to emails, to like Yammer social. We pick Kafka again from a scaling point of view, it's distributed at scales really well. So they all go into separate kind of Kafka topics. We Spark streaming then, we'll pull the data from then, it will do some cleansing of the data, it might do some joins out to another system, it might do some joins in Cassandra itself to enrich the data from another kind of metadata table or something like that. It will store it in these big, massive, bulk, raw tables. And it was those raw tables that were killing, and they still are, killing our MySQL database. For our main application, the bulk of the data is that raw click data, raw feeds. So that's slowing down everything, and we're hoping now, we're pretty shortly going to migrate those fully onto the new infrastructure. So everything is in there in raw, the data, we use Cassandra as well, they're a very good fit. Spark sits, it's co-located with Cassandra, and there's a lot of speed advantages and things like that. Then we've kind of Spark jobs that run, batch jobs that run, they're running constantly 24/7, that are taking that raw data again, joining it more, maybe doing different things, filtering out all the operations that I'll go into in a minute. And then it writes them into these kind of lookup tables in Cassandra, which means everything is pre-processed, everything is, so a batch you might get one click in, it might split it into, depending on the metadata of, say if I clicked, I'm in development department, the typical kind of Google Analytics segmentation that you might be familiar with. And so we've it all ready to go, and our front end is ultra responsive. It's just like, oh, you want that metric, Rand, you want to deliver, you want a new widget, here you go, the data is there. There's a whole similar Docker and Kubernetes and all, just sit here on top of that. So that's where we ended up. But back to Spark, that Spark core that I talked about, that simplicity, is all based on one concept, which is the resilient distributed data set. So your man Matty came up with this, which is basically a collection that's distributed across the machine, or across a cluster. But its main properties are, and it kind of goes back to functional programming, they're immutable. Once you create one, you can't change it. You can create another one from it, which makes distribution a lot easier. They're lazy, they're not computed till they're needed. Again, if anyone's into functional programming, that's a familiar concept. It's not that familiar to me, but they're fault tolerant. If the RDD has multiple partitions, if one of them gets blown away, if a machine goes down, Spark can recreate it on another machine. And again, the most important thing, they're distributed over cluster machines so they can be operated on in parallel. So they're created by parallelizing a collection here. I've got an array, I can go my Spark context inside of my code, spelled wrong, parallelize this data. That will take that and it will return an RDD. That array is now split over 1 node, 100 nodes, 1,000 nodes, depending on the size of your cluster. You don't care. You don't know, doesn't matter. You can also read data in from external sources, like I said, Cassandra, from files, from databases, from Hadoop, from HBase, from Kafka. There's all like, and they're all literally 1 or 2 liners that you're like, okay, now I have my data, it's in memory, it's on the cluster, I can now go from here. And the second part then of Spark Core is those operations that you can apply to RDDs. So because they're partitioned to cluster, each partition can be operated on in parallel. They support 2 types of operations, a transformation, which creates one RDD from another. Map, flat map, filter, like anyone who's worked with collections in any language will be familiar with these concepts. You're taking that knowledge, you're not worrying about that it's distributed, you're not worrying about that like that. You can just RDD that, filter, group by, reduce by key. So here's one, it reads in a text file. That'll give you an RDD of that text file. It'll go text file.flatmap, so that'll give you, it'll take each line in the file and it'll split it, and flatmap will give you a flattened list of all the words in the file. Then you'll map the word to word and count 1, and then you'll reduce by key in the word, and that'll go 1 + 1, and it'll output the word count for each of the file. So that's 4 lines. I think if you look at that in Hadoop code and Hadoop Java code, it's a lot more than that. But again, it's quite familiar. People might be used to reading flat map. It's readable. You're not worried about that complexity underneath it. Actions then are the second part of it. So because they're lazy, Spark actually doesn't do anything. This is your driver code. It's just one file, one main method if you want to. Until it sees an action, it doesn't do anything. It records the set of instructions to create the final RDD. And then when you call an action, it'll work backwards and it'll materialize the RDD. And I think I have that picture here. So that's kind of the left-hand side is that driver code. You take your input, you create an RDD, you apply some transformations and filters to it. And then you do an action like you might collect back the RDD to your driver, which will give you an array. You might count the number of results in the RDD. You might save them out to Cassandra. At that point, Spark has built up a direct cyclical graph, which is basically a set of instructions of how the data transforms. It breaks that up into tiny little tasks and stages, and kind of it's more low level now. I'm going here, but it'll split up that RD, gets partitioned. So there's 1, 2, 3, 4 partitions in that. It'll operate each of those transformations on the partitions. It'll split out all those mini jobs across the cluster, and it'll know to bring it all together again to give you, say, a count or to save it to Cassandra. So it kind of works backwards. And that brings its own challenge about troubleshooting debugging, because it's not like, oh, I'll set a debug point here when, I'm here. I'll see what my counts is like. There's nothing there. You've just got this RDD. It's until you do a collect on it, which will bring back an array, you won't be able to expect the elements. So it builds up this DAG, this kind of set of instructions. And again, why that's important, because if you lose a partition, it has that lineage. It knows the set of instructions to get back to this partition again. So it'll recreate it. So yeah, under the hood, I just wanted to kind of take one of the operations, one of the transformations you could use, and go into a small bit of how Spark, kind of what it does underneath the hood. And anyone using MapReduce will be used to this terminology as well. So reduce by key. Say you have a load of code before this, and you end up with a data set that has Messi and Ronaldo's goals scored over the last 3 years. So this is your RDD at this point in your code. You want to get the total goals for each guy. So you've got 3 machines in your cluster. You've got 3 partitions in your RDD. One partition calls, has got 2 from Messi, 1 of each of them, and 2 from Ronaldo. It'll do a map side reduce first. So it'll try. This is the expensive bit in Spark. So when you're writing Spark code, it's like you're writing normal Scala code or Java code. It doesn't seem any different. But how Spark break things up, there's certain operations are expensive that you want to, you might want to prepare your data in a certain way to reduce the number of shuffles. So what has to happen is Spark will go, I'll reduce this, I'll add the 2 of them, so I'll have Messi and I'll add the 2 goals. I can't reduce here, and it'll reduce here. So now we've got half the data. Obviously, to reduce, all Messi needs to be in one machine to get a count for Messi, and all Ronaldo needs to be on another machine. So it has to shuffle the data so that they're all on the same node. It'll do as much processing as it can on each node, and then it'll transfer the kind of pre-reduced data over to the nodes here, and it'll do the final addition there. So why that is important is these shuffles are super expensive. All this happens in memory. It's lightning fast. Any maps you do, any filters, they're really, really fast. But any operation that requires a shuffle, it has to write to disk. The same with any distributed system. It has to write to disk, it has transferred across the network, and it has to read it back in. So that's kind of one of my learnings, that it's like writing Scala or Java code, but there are considerations. Certain operations are expensive. you might want to rejig your code, not exactly how you would write it normally. That Spark though has tooling, it has a nice UI to allow you to get the bottom of things like that. You know, you can see a running application here. These are stages. This is how it's split up. You've got a for each there, you've got a flat map, a for each, a flat map. It's actually split up that could be a couple of lines of code, and it's split it up, it's distributed across the cluster. You can see how long each one takes. You can actually click here and see this line of source code that caused this task to be spawned across the cluster. So you can really, you can really get an insight into tuning your apps, and you can learn a lot about Spark from looking at the UI. Here, for instance, you've got 2 RDDs. I've parallelized 2 collections. It's come down here, it's done some mapping. Then you've got a function which brings it to it. So this is happening in parallel. Even though your code, you look at it, you wouldn't even know that. Spark has gone, yeah, I can do the 2 of these in parallel. There's a join here, the 2 of those. There's a type of join. So it shuffles them to do a join. It needs to do a shuffle across the network to get the same keys, you know, to join on the same machines. Does that again, all in one machine then. And that, you know, there could be within this, there could be loads of tasks happening in parallel. And then it has to do another, say, shuffle to do an aggregation. So that's how, you know, that's that directed cyclic graph I talked about. That's the history of how you go from your raw data to your final count. And Spark has the tooling to give you that insight into, okay, you wrote this code, here's what Spark does with it, if you do want to look at it. And I find it's a great way of learning about what the code actually does. How we develop Spark apps, obviously with data, with lots of different data, you might have assumptions, you might go into a meeting, you might have an idea that said, geez, this is a great idea. You know, Spark is this massive tool set, I'm sure there's something in there that I can do it with. Normally we'll do a text spike, we'll kind of prove our assumptions about the data. Can I get the data? What kind of format is it in? Spark has a nice REPL on the command line where you can, you know, just command line, you can fire up a Spark context, it'll run locally on your machine, you can try out different transformations. You can write a little quick app, we have a little shell of an app, and then we put in what code we need. We can test out those assumptions about the data. Will it give us, is it possible to get to the desired outcome that we want? There's also a product, open source tools like Apache Zeppelin or Spark Notebook, where you can actually sit them on top of your production Spark cluster, and you can just type in ad hoc commands, you can build up nice dashboards, again, around data exploration. Once we're happy that we're going to deliver, you know, this is going to be a runner, it's going to give us something for our product, then we'll develop it. We'll develop everything in local mode. So basically on your machines, there's back to TDD, there's nice test harnesses in Spark. It's really nice to develop with. We'll build it up locally, we'll have unit tests. We found acceptance tests very important because you come back to an app later and you're going to go, oh, what metrics what dimensions are we dealing with here? So we found those, that we use feature spec, but you could use Cucumber, things like that as well. Those very, very important. Then we'll assemble a jar and like we're done, we're dev complete. But at this point, you might get the right answers, as in your unit tests will pass, you're happy that your transformations, given a particular set of data, will give you the right output. But performance-wise, because of what the considerations around the reduces and shuffles, it could destroy your cluster. We had one example of inside in a for comprehension, someone put in a reduce by key. So it was generating shuffles. You'd go onto Spark UI and you'd see shuffle, shuffle, shuffle for like hundreds of thousands of shuffles. If they'd wrote the code slightly differently, they'd have done their for comprehension, whatever they need to do, they would build up maybe a bigger data set, maybe slightly less, traditionally less efficient. But when it comes to Spark, it was a winner, and it was a simple fix to pull that out, to do some kind of pre-organization of the data, and we solved that problem. So to alleviate that, we run a distributed test, and again, back to Docker. We set up a Spark cluster in Docker. If it's a streaming app, we'll have a Zookeeper, or not Zookeeper, we'll have Kafka, nodes in Docker, containers in Docker as well. We'll pump in the raw data, and again, it takes time, like Luigi said, to these considerations around load testing. But they're very much worth it, because number one, you learn a lot by putting that data through the system, looking at the Spark UI through Docker. You'll see, okay, what exactly is going on here? Yeah, most of the time it's absolutely fine, but I've always found I've learned something. I've tweaked the code in a certain way, like there's things like broadcast variables that might save you a shuffle. You can broadcast smaller data sets around, and just generally tune the app. And then we deploy the production to the production cluster, and we monitor. And like you said, there's great monitoring in Spark. We pump it out to it does out of the box. It'll write metrics to graphite, and again you get all the figures you want. So general tips, remember it is distributed under the hood. So yeah, the API is lovely. And again, back to what I said, you think it's great, you're writing away, it's fine. But if you're writing batch applications, it is MapReduce code. It's not using higher order functions. You might think, oh, I'll reduce by key. I know how this works in, I don't know, flat map. I know how this works in Scala. But underneath, I know what the Scala compiler does, but Spark is very different. It behaves differently. You might break up a flat map totally differently to how you expect it. So the job in reading the Spark docs is to reduce the number of shuffles. That's how you get the most performance. And hence the ordering of operations matter. Another one, remember it's distributed. It's a bit, this is your driver code, you've created an RDD, and you've also got a variable called counter. Then you've got an RDD.forEach, which is just a function to loop over the entries in an RDD. Inside there, you've passed in an inner function to say increment the counter. Spark is going to take that line, that function is going to create tasks and distribute those tasks across the cluster. Hence, counter is going to be distributed across the cluster 5 times. So each executor on the node is going to be doing its task. It's going to increment its own value counter. I don't even know what that, if you were to print that out after, I don't even know what it would turn out like. But there's little subtleties like that you might get someone maybe inexperienced in or your first time doing it. It's key to watch that. The solution for this, you'd use a broadcast variable. Everyone gets a copy, but it's actually the same variable, and you can increment away. And Spark also has accumulators that get broadcasted out to the cluster, and hence you'd solve a problem like that. Again, to repeat what Luigi said, BDD and TDD are super, super important. You can be chaining these operations together. You could end up, where am I? I thought I'd be here. What exactly is this data? So we tend to write and we break out those. We don't chain many functions together or many of those transformations together. We tend to take one or two that performs a single unit of work, a logical unit of work. We'll wrap tests around it. Again, it's very easy to mock up the RDDs, pass them into the function, and assert on the RDDs. Like it's really good, and it's definitely paid off for us, because remember the first few apps we wrote, you'd have just a ream of kind of linear code, and you would know where you are. You'd have your end-to-end test, but to actually break it down to the individual bits, it definitely speeds things up. Our take so far, kind of on the negative, it's not fire and forget. Back to what I'm saying about tuning the apps. It's not like you write it and boom, it goes onto the cluster and you forget about it. Like you are open to kind of writing, funny things. And you do kind of, from an operational point of view, there is like running any distributed cluster, any cluster of any type, there is overhead in it, regardless of Hadoop or whatever. So for me, that was a massive learning in terms of like DevOps. You're going in, you're looking at, okay, how many CPUs, how many apps are running, how many cores do they get, how much memory does each app get, how do we control those resources? There is resource managers like Mesos that will do that for you, but we are running it in the most simplest cluster possible at the moment. There's a lot of moving parts in the cluster. You've got drivers, executors, workers, different machines. So troubleshooting, again, when you're scaling these things, where did the logs go? How do you find out who was wrong? We put everything back to Logstash, and we have Kaban on top of it, so we're in a good enough situation now. But it wasn't like that at the start, and you're, again, going onto machines, and you're trying to find where the logs for a particular run of an app went. Also, understanding these moving parts, like what's their purpose? Where would I expect this to break down? If this was to run out of memory, would the executor run out of memory? Would the data be there? Would the data be pulled back from the driver? Someone might put in an action to collect an RDD of a couple of gig or tens of gigs. In one line, you could pull that all back to the driver will crash. So there is a kind of a level of understanding and education around it. But again, the Spark UI gives you the tools to look at what's the size of the data in memory and all that. On the positive, the scalability has been great. You can add another cluster, add another machine, you're grand. The flexibility, the API is unreal, like going from streaming to batch to whatever. It's the same API, it's very familiar. Once you're up to speed in one, you can kind of get gains in the other areas. And I say it's really, really nice to work with. The streaming has been very, very stable for us at the start. We were a bit iffy about the streaming, but it's really, really good. The Spark UI has been great, and again, DevOps, it kind of sucks you into that, understanding the cluster, understanding how the code works, understanding the different processes that are involved. And hence, I feel I've written better code from it than I would have if I just written a bit of Java and forgot about it. And conclusion, so the product, that architecture, is in production since April and it's going well. And I say we're hoping to migrate the existing reports off the old infrastructure pretty soon. We now have multiple teams using Spark, and developers generally, well, all of us really like using it. And again, even if I wasn't using big data, I'd actually still use it. Like, the API is really, really nice. And we want to expand our use of Spark to other areas, such as the kind of data science, those ad hoc investigations, maybe machine learning, if we can, even just to play around with a few things. It's kind of all there, and once you know the API, you kind of have that confidence to go, oh, it's just dealing with data sets, it's just, it's dealing with RDDs, oh, this is another function. I can, the machine learning, it's like train it up the data set, use use whatever algorithm they have and test out the results. So we kind of want to expand it further. I think we are going to expand it to more teams and more use cases in the future, which is pretty good. So yeah, that's me. Any questions on Spark or on how we use it?
Smell the pizza, so just one question maybe. You have this variety in your data. What's your approach to I suppose normalizing the data? Are you, when you're trying to get insights into how customers are reading things, are you creating a data set of email views and video and a separate data set of video views?
Yeah.
Have you normalized things at some point?
And even within that, within Cassandra, we denormalize further. So you might have, say you get in your email stream, you take those in, you might write them out. Depending on the end use case of how the app would want to use it, we might even write that out into separate tables and denormalize it further. But yeah, we have a kind of different data set for each of the kind of the inputs into our system.
Gotcha. So,
yeah.
So your, I suppose, one insight might require queries against several different data sets.
Yes. Yes. Gotcha. Yes. Yeah. Yeah. And yeah, it's that kind of joining, and you'd manipulate the data into a certain key value pair. So you'd work a lot with MapReduce and key value pairs and things like that. Like a lot of it, even with the streaming, a lot of our batch apps, I could probably go and re-implement them in streaming. Is that performance? And you see that's a common pattern, that kind of lambda, where you'd have the streaming would do the intermediate results, and then you have a batch app will clean it up at night. So your real time would allow for a certain amount of error. But again, it's because it's the same code. You can use the same code that we've written in our batch. I can take those functions and use them in the streaming. So that investment is not, because the streaming is actually micro batches, it's micro RDDs. So it's the same thinking. So we can do it in batch, which is more conservative. Then we said, you know what, we might try that in a streaming app. And often you'd see on the web, you'd see in the same project, you'd have a streaming aspect and a batch app and a batch aspect to it. So they'd both do the same processing, but one would happen, like the batch would happen afterwards. So, yeah.
So I presume you have pizza at the back of the room there, so help yourself, and thanks again to Newsweaver for sponsoring.
Thanks, Dave.